Hey guys, my name is Alistair Louise and welcome to this video where we will explore the problem of class imbalances. One of the common roadblocks faced by machine learning engineers are class imbalances. So in this two-step tutorial, that is this video and the next, we will explore the problem of class imbalance and discuss the strategies to handle them. So if you have worked with machine learning projects in the past, you may have come across imbalanced datasets. Imbalanced datasets are those where the distribution of classes are significantly skewed. What does that mean? It means that one class is being more dominant while the others are underrepresented. Because of the skewness in data, it poses a very unique challenge to machine learning engineers to build an effective machine learning model on top of this data. So in order to make this concept very comprehensive, I have split the tutorial into two parts. In the first part of this tutorial, that is this video, we will explore various metrics used to effectively evaluate imbalanced datasets. We will also see how better these evaluation metrics are when compared to accuracy. So what are these metrics? So the ones that we will cover in this tutorial are precision, recall, F1 score, and ROC curve. And in part 2, that is the next video, we will conclude by exploring various strategies that we can use to overcome the class imbalance problem. This will in turn improve the performance of our machine learning models. There are three different ways in which we can overcome the class imbalance problem that we are going to cover in the next video. That is the resampling technique, ensemble methods, and cost-sensitive learning. We will be using the following libraries in this tutorial. Besides the usual four, that is pandas, scikit-learn, plotly, and numpy, we will also explore how imbalanced learn can be used to overcome the class imbalance problem. So let's get started. First, let's install and then import the necessary libraries required for this tutorial. So I'm going to be creating a dummy imbalanced dataset for this tutorial. So I start by setting a random seed so that the results shown are reproducible. And then I define the number of instances that needs to be present in the data frame. So I set it to be 1000 rows. And then I set a class imbalance ratio of 0.8 or 80%. So in my data frame, I want to have two columns. And one of the columns is called the fruit column, containing two different possible values, which are apples and oranges. And then in my target column, I will have 1 and 0. And I set an imbalance ratio earlier, which is 80%. So 80% of the values would be 1 and 20% would be 0. And then finally, I create the pandas data frame with the two columns. And the names are fruit and target respectively. So let's just print out the data frame to see and verify the data. So let's just plot out the value counts of the target column using plotly. And as you can see, this is exactly what we want. Out of the 1000 instances, we have 800 that belongs to class 1 and 200 belongs to class 0, creating a class imbalance. Since we have our dummy dataset ready, we move on to the next step, that is to perform binary classification on this data. So before we do that, it is necessary that we encode the categorical column fruit, since right now it contains two distinct values, that is apples and oranges, in the string format. We know that machine learning models can only understand numbers, so we need to convert these strings into numbers, and for that we use encoding. A detailed guide on encoding strategies is covered in one of my previous videos, and I have linked it here in the notebook. I've decided to use the simplest encoding strategy, that is label encoding, in this tutorial. So let's run the cell which will label encode our fruit column. And let's print out the data frame now containing the encoded values. You can see that we have a new column called fruit encoded, consisting of zeros and ones. The zeros represent apples and ones represent oranges. Now let's split the data into training and test data sets. The training data gets fit to our machine learning model, and we will use the test data to evaluate the performance of the model. We can see that the xtrain is just the fruit encoded column now in a numpy array format. So let's print out the shapes of the train and test data sets just to verify that everything is in fact correct. Then I will be reshaping the xtrain and xtest series into the shape -1, 1. Now printing out the xtrain series, you can see that the array that has been reshaped is of this format, where each input value is present in a separate row. This is exactly the format scikit-learn's logistic regression model expects the inputs to be. Okay, so let's initialize the logistic regression classifier and let's fit it on our trained dataset. Okay, since we have fit the model to the data, let's also make predictions on the test dataset and store it in the ypred variable. We will be using these predictions soon to evaluate the performance of our logistic regression model. Alright, so since we have our predictions ready, now is a perfect time for us to go deep into identifying different metrics that we can use to evaluate the performance of our model when trained on an imbalanced dataset. So as I mentioned previously, we will be going through accuracy, precision, recall, and F1 score. very soon. But before that, it is important for us to understand the concept of a confusion matrix and that we demystify the confusion behind confusion matrices. So let's see what a confusion matrix contains. In this illustration shown here, this is an example of how a confusion matrix looks like in a binary classification problem. Similar to what you have done in this tutorial, which is also a binary classification problem, we have predicted labels, which is 1 and 0, and actual labels, which is 1 and 0. And we can also see that there is a square that has been divided into 4 cells, with the top left containing the number of true positive values, top right containing the false negative values, bottom left containing the false positive values, and bottom right containing the true negative values. To understand what these values are, let's take an example. Okay, so let's take this example. So let's say you're building a model that will predict whether the given input is a cat or a dog. And we can see that the rows contain the actual values and the column contains the predicted values. So let's say that your model predicted a cat and the actual value is indeed a cat. So in this case, this is a true positive example. And this is shown in the top left cell, where it says that there are 3 cases in this example where the model predicts that a cat is indeed a cat. So let's take an example where the model predicts wrong. So the model says that it is a cat, but the actual value is a dog. This is a case of a false positive example, as you can see in the bottom left cell. So in this example, you can see that there are 2 cases where the model gets it wrong, says it's a cat, but actually it's a dog. And this is also referred to as a type 1 error. So let's also consider the reverse scenario where the model predicts it's a dog, but in reality, the actual value is a cat. This is an example of a false negative case, and it is also referred to as a type 2 error. And you can see this in the top right cell, where in this example, there is 1 case where the model gets it wrong, and it's a false negative. And the last case is a true negative example, where the model predicts the negative class, and it is in fact the negative class. So in this example, the model predicts that a dog is actually a dog. This is shown in the bottom right cell, where there are 4 cases where the model gets it right in predicting a dog, where in fact it is actually a dog. So let's summarize the results one more time and interpret the results. For a true positive example, the interpretation is that you predicted positive and it's true. So in the above example, that you predicted a cat and it is indeed a cat. And a true negative case, the interpretation is that you predicted negative and it's true. So in the above example, once again, you predicted that a dog is indeed a dog. Now what about type 1 error, that is a false positive example? The interpretation is that you predicted the positive class, but it's wrong and it's false. So in the above example that you predicted it is a cat, however, the actual value is a dog. And last but not the least is the type 2 error or the false negative example, where the interpretation is that you predicted negative and it's false. In the above example, you predicted that it's a dog, but in reality, the actual value is a cat. Using what we have learned in the previous section, let's apply it to our data and see what the confusion matrix looks like. So scikit-learn offers 2 useful functions when it comes to getting the confusion matrix and displaying it. And as you can see, it's pretty simple. All you need to do is call the confusion matrix function and pass in the test and prediction series. And then I've manually assigned the labels to be 1 and 0 as we have used in our data, and then passed it to the confusion matrix display function. As you can see, the model does a pretty good job in predicting the true positive class correctly, and 162 times it gets it correct. Whereas the false negative is 0 and the false positive is 38. And the true negative is also 0. So the model's prediction is not the best. However, when it comes to predicting the positive class, it does a pretty good job. So now let's move on to the first evaluation metric, which is the simplest of them all, and you would have probably heard of it, and it is called accuracy. Accuracy can be defined as a ratio of correct predictions to the total number of predictions made by the model. So the formula can be seen here, where it is basically just the number of correct predictions divided by the total number of predictions. Applying the accuracy score function to our model, we can see that the performance of our model seems to be pretty good, and 81% of the time it gets the prediction correct. However, do not be misled by the score and always take the accuracy with a grain of salt. The reason for this is that we know our dataset is imbalanced and the ratio of 1s and 0s is 80 to 20. So even if the model predicts 1 randomly, it gets it correct 80% of the time, and hence the accuracy score is definitely gonna be high. And this is why we need alternative evaluation metrics that gives us a fair estimation of the performance of the model when working with imbalanced datasets. The first alternative is precision. Precision can be defined as from all the classes which we have predicted as positive, how many are actually positive. So the formula as seen here is basically true positive divided by true positive plus false positive. And as usual, scikit-learn has a built-in function to calculate precision. We can pass in the test and prediction series, and printing out the precision, you can see that the precision score is also 81%. But let's not call it a day just yet. Precision just gives us a one-dimensional view of the performance of our model, and it is necessary that we also take into account other evaluation metrics before we finalize how good or how bad our model is. And that is why we need this metric, which is recall. Recall can be defined as from all the positive classes, how many of them have we predicted correctly. So recall is also known as true positive rate. So the formula is true positive divided by true positive plus false negative. So let's use scikit-learn's recall score function to calculate the recall for our model. Surprisingly, the recall score is 100%. So in this case, the positive class, which is 1, is being predicted correctly all the time. So looking back at the confusion matrix, we can see from this diagram that the precision and recall can be calculated directly from the confusion matrix. And we know that recall is basically true positive over true positive plus false negative, as you can see from the red square, and precision is true positive by true positive plus false positive, as you can see by the green square. So we have seen what precision and recall is, and as a machine learning engineer, I can say that it is very difficult to compare two models with low precision and high recall or vice versa. So there's this pretty useful evaluation metric known as F1 score, which is personally my favorite and what I use to evaluate my machine learning models. F1 score basically uses harmonic mean between precision and recall and punishes the extreme values. And if you're aware of the harmonic mean formula, it can be seen from this formula of F1 score, where it is 2 times recall and precision divided by recall plus precision. Once again, scikit-learn has a built-in function to calculate F1 score, and you can see that the score is 89.5, which, if you can cross-check, it is the harmonic mean between precision and recall. Okay, since we have seen accuracy, precision, F1 score and recall, we might be inclined to conclude and say that the model performs really well on our data, since we have around 81% accuracy and 89.5% F1 score. However, let's still not call it a day, since we have one more metric to cover, which is the ROC curve. So what is an ROC curve? ROC stands for Receiver Operating Characteristic, and it is a graph that shows the performance of a classification model at all classification thresholds. So the plot has two parameters. That is the true positive rate, as you can see from the y-axis, and the false positive rate, as you can see from the x-axis in this illustration. So this illustration tells us how we can evaluate a model to say whether it is good or bad based on the ROC curve. So you can see that the model gets better the closer it gets to the blue point as shown in this illustration, and a random classifier would be just a straight diagonal line as shown by the red line in this illustration. So let's print out the AUC ROC score, which is a function that is offered by scikit-learn, and you can see that the score is 50%, indicating that the model that we have built is as good as a random classifier. This seems to be pretty odd, since we got a good accuracy and F1 score. However, the ROC score seems to be just 50%, meaning that it should be a straight line, indicating it is a random classifier. So scikit-learn gives us a ROC curve function, which we can simply use to get the false positive rate, true positive rate, and the thresholds, and this can be directly passed on to Plotly to plot the ROC curve. So plotting it out, we can see that the ROC curve is just a straight diagonal line, indicating that our model is just as good as a random classifier. If we would not have considered the ROC curve, we would have concluded the experiment by saying that the model performs really well on our data, since we have pretty good accuracy and F1 scores. But only once we have plotted the ROC curve did we understand that our model is performing poorly in terms of distinguishing between the positive and negative classes. This is because the AUC ROC score is 50%. So the ROC score being 50% typically occurs when we have an imbalanced dataset, or when the classifier is not able to capture the underlying patterns. While we know that since we have an imbalanced dataset, this would be the reason why the model is performing poorly. So this brings us to the end of part 1 of this tutorial. We can see that working with imbalanced dataset is a tricky situation for any machine learning engineer. You can never conclude that the model is performing very well on the data until and unless we have thoroughly evaluated the model using all the different metrics that we have discussed today. Now, since you have seen different metrics that we can use to evaluate the performance of a model on an imbalanced dataset, there are different strategies that we can use to improve this performance and overcome the class imbalance problem. This is going to be the topic of discussion in the next video, which is the part 2 of this tutorial. So stay tuned for the same. And I hope you have found this video useful. And if it did, it truly means the world to me. Please leave a like and subscribe if you have enjoyed this video. With that being said, I hope you guys have a great day. Take care and peace.